Good morning and welcome to today's class. Today we will discuss about the surfaces. In your multivariable calculus classes note, you have studied what is a surface. Here we are dealing surface definition in differential geometric ideas. First of all, let us move to the definition of surface. A definition: a surface of dimension n, a surface of dimension n, or an n surface in Rn plus 1 is a non-empty subset S of Rn plus 1 of the form S equal to F inverse of C, where our F defined from some U to R, where U is open in, where this U is open in Rn plus 1. And F is a smooth function. F is a smooth function with the property that del f of p is not equal to 0 for every p belongs to S. So this is the definition for surface. So a surface of dimension n or an n surface in Rn plus 1 is a non-empty subset S of Rn plus 1 of the form S equal to some F inverse of C. That means this S should be a level set of some constant C, where this F defined from U to R, U is an open set in Rn plus 1, and F is a smooth function with the property that del f of p is not equal to 0 for every p belongs to S. So let us have some examples. A one surface in R2. A one surface in R2. So what it should be? One surface in R2 should be this is R2, right? So in that we should consider a one surface. So one surface means it should be a subset of R. So anyway, one surface in R2 will be a curve. Is called a plane curve. It's called a plane curve. If you are taking a two surface in R3, what it should be? Is usually called a surface. Is usually called a surface. So this is your example, or not one. First example, we can take a one surface in R2 is a plane curve. A two surface in R3 is usually called a surface itself. Now generally an n surface in Rn plus 1 is called a hypersurface. An n surface n surface in Rn plus 1 is called a hypersurface when this n is greater than or equal to 2. Okay, so this we have already seen that what is a hypersurface. Hypersurface means subset which is having dimension less than 1, right? If it is an n dimensional space, if you're taking an n minus 1 subspace, means that should be a hyperspace. So in the same way we are considering the surface. When you're having an n surface in Rn plus 1, then this n surface is called, what is the dimension? 1 less than this Rn plus 1. So this is called an hypersurface. So as a remark, it's combining with your previous theorem. So remark by previous theorem, each n surface S has at each point P belongs to S, a tangent space which is an n-dimensional vector space, vector subspace of Rpn plus 1. So vector field at the point P, that is Rp n plus 1. And this space SP, we are naming that as SP, depends only on the set S, not on the function f, right? On the set S, and it is independent of the function, f. What is this f? We are used to define your surface, comma, which is used to define the surface S. So by previous theorem, what it says is that if each surface you are considering, you can have a tangent space at that point. Okay, so we can have a tangent space. Now this tangent space is of n-dimensional vector subspace of Rp n plus 1, and this space Sp depends only on the set S, and it is independent of this function f. This we have seen in your previous class. So here we are having examples. Here already we have considered one example. So this is example 2. The unit n sphere. What is the equation of unit n sphere? It's of x1 square plus x2 square plus x3 square plus etc. plus xn square equal to 1, or xn plus 1 square, because we are taking in rn plus 1. So it is xn plus 1 square equal to 1. Now we want to show that this is a surface. So for surface, what we have to do? We have to define an f from rn plus 1 to or from u, okay, rn plus 1 or u to r, right? And we want to show that this can be written as some s equal to f inverse of some c. So this is our aim. So how to show that? We can write this as something like f inverse of 1. So it's very easy. You consider the function f of x1, x2, etc. xn plus 1 equal to what I should consider? x1 square plus x2 square plus extra plus xn plus 1 square. Now evidently this can be written as f inverse of 1. Then f inverse of 1 is the end surface since we want to check one more condition. We want to write this, and we want to check del f of p not equal to 0 for every p belongs to S also, right? So we are checking that since is an end surface, and since what is del f of p? Some del f of p when you're calculating means it should be 2x1, right? 2x2 extra 2x n plus 1, right? P comma, so this should be your del f of p. Now this equal to 0 implies your x1 equal to 0, x2 equal to 0, etc. xn plus 1 equal to 0, right? Now if this is the condition, means what you're having is x1, x2, etc. all are equal to 0. That means your x1, point x1, x2, etc. xn plus 1 is equal to the origin, right? But when you're having x1, x2, x3, etc. equal to 0 means definitely it will not satisfy this equation, right? That means whenever your del f of p equal to 0, then this point does not belongs to, which implies your x1, x2, etc. xn plus 1 is does not belongs to S, right? So here we can conclude that it's an end surface since del f of p not equal to 0 for all p belongs to S. So we have proved that this unit sphere in is an end surface. So hope you understood how to prove this, right? So we can take a second example. Second example is, let a1, a2, extra an plus 1 belongs to rn plus 1. That means this is a point in your rn plus 1, and further condition is given as a1, a2, extra an plus 1 is not equal to 0. That means this is a non-zero point. And let some b belongs to R. That means b is a real number. The n plane, we can define that as a1 x1 plus a2 x2 plus extra plus some an xn plus an plus 1 xn plus 1 equal to b. Okay, a1 x1 plus a2 x2 plus extra plus a n x n plus a n plus 1 x n plus 1 equal to b is a level set, right? Definitely it will form a level set, f inverse of b. So is a level set f inverse of b, where f of x1, x2, etc. xn plus 1 equal to what it should be? a1 x1 plus a2 x2 plus extra plus an plus 1 xn plus 1. If this is the function, means we can express this n plane as some f inverse of b. Then it is an n surface. Then it is an n surface. It's an n surface for each b belongs to R. For each b belongs to R. What's the condition? We have expressed this as a level set, but we want to check one more condition. What is that? Del f of p not equal to 0. Since del f of p not equal to 0, so we can write, since del f of p is equal to del f of, I can take x as p as x1, x2, x3, etc. xn plus 1. Now what it should be? When you are finding del of this, means it is nothing but x1, x2, etc. xn plus 1, that is p part is over. Now I want to have the derivative, right? So it is nothing but a1, a2, etc. an comma an plus 1, and we have assumed that this a1, a2, etc. an, this part, where is it, is not equal to 0. We have assumed, right? Yeah, see here, we have assumed that this part is not equal to 0. So what you're getting is this one and this one is not equal to 0 by our assumption, right? If you want, means you can keep that as some star marked one, and this assumption as you mark it as some star marks. Okay. So what you are getting is this also will represent a surface. Now a plane, we can note this, not a plane is usually called a line in R2. A two plane in is usually called what is called usually called? It's simply a plane, right? A plane in R3. For n greater than 2, an n plane in Rn plus 1, this we have already seen, is called a hyperplane, right? Called a hyperplane in Rn plus 1. Since we have seen in surface, we have seen this, so we are having the same terminology when it is a plane also. Next we are having few more examples. Before that, we can have some interpretation of this. Suppose we are having this surface. Okay, so I'm taking that surface as before. So when you're having two values, not 2, this we can have not 1, and this not 2. Two different values of b, two different values of b with the same value of a1, a2, extra an plus 1. Define parallel n planes. Define parallel n planes. We can check it, right? For example, we can have let f of x1, x2 equal to, I'm taking here a1 equal to minus 1 and a2 equal to minus 2, right? So it will become minus x1 minus 2x2, right? Okay, now when you're having this f inverse of 1, b I am taking as b equal to 1 and 2, or 1, you can take 1, 0 or minus 1 also. So what this will come, let us see. So our idea is f of this equal to b, right? So when you're drawing this, what you're having is for f inverse of 0, what it should be, f inverse of 0 means you will get this quantity is equal to 0. So f inverse of 0 implies what you're having is minus x1 minus 2x2 equal to 0, right? So what you're getting is x1 equal to minus x1 equal to or minus 2x2, right? So this is the line. So this line means evidently it passes through 0, 0, right? So the line passes through 0, 0. So this will be the line. Secondly, when you're having f inverse of minus 1. So f inverse of minus 1 means it will be somewhere here, because f inverse of minus 1 means this should be equal to minus 1. So 1 minus something will come. So this our f inverse of 0, and here will become your f inverse of 1, right? F inverse of minus 1. Now f inverse of 1 when you are taking means it should be somewhere here. This you can check it, just to draw this in a graph. Then this should be f inverse of 1. So anyway, you are getting some parallel lines. So same way, when you're having higher dimensions, this will become planes, right? For n equal to 2, when you're considering, for n equal to 2, we are getting f of x1, x2, x3, right? 3 dimensional space. This should be minus x1 minus 2x2 minus 3x3, right? Then when you're drawing this picture means it will be something like a plane may come something like this. Now another parallel plane will come somewhere here. It may come something like this. Then we will get another parallel plane. So like this, so many planes we will get, right? So this may be a drawing this axis, means it may come something like this. Okay, now this should be your f inverse of 0. Now this should be your f inverse of 1, and this one should be your f inverse of minus 1. So something like this we will have. So anyway, in your previous example, when you're having fixed values for a1, a2, a3, extra an plus 1, and different values for b means we'll get parallel planes. That's the idea. Now here is an example 3. Sorry, example 4, right? So example 4, let f from u to r be a smooth function, be a smooth function on u, comma, u open in Rn plus 1. Sorry, u open in Rn we are considering, right? So u open in Rn. The graph of f, we have already defined what's the graph of f. So the graph of f, comma, I'm mentioning that as graph of f, that should be equal to set of all x1, x2, etc. Since I am taking in Rn, it is of xn plus 1, which belongs to Rn plus 1, such that my xn plus 1 is equal to f of x1, x2, etc. xn. Right? So this is the idea of a graph. Now this graph is a n surface in Rn plus 1. Now this one is a n surface in Rn plus 1. Now since graph of f can be written as, since our graph of f can be written as some g inverse of 0, where I want to define what is this g, right? Now what should be the g, can you guess? My g should be g of x1, x2, etc. xn plus 1 equal to xn plus 1 minus my f of x1, x2, etc. xn. Is it clear? So when you are having a graph of a function, that graph of a function can be treated as an n surface by taking your g as xn plus 1 minus f of x1, x2, etc. xn. Now this is we have expressed this as a level set, but we want to check that whether del g of x1, x2, etc. xn plus 1 is not equal to 0 or not. Okay, let us see how we can find it. Also del g of x1, x2, etc. xn plus 1, what it should be? This of point, first of all the point x1, x2, etc. xn plus 1. Next thing is we want to find the derivative, right? So for derivative with respect to x1, partial derivatives only. So minus f of something. So partial derivatives of dou f by dou x1, again minus dou f by dou x2, etc. How much will come? Dou f by dou xn, up to here. Now I want to find the derivative with respect to xn plus 1. What is that? It should be 1, right? This derivative, partial derivatives of g with respect to xn plus 1. xn plus 1 is 1. And this value is not equal to 0, right? Because this one non-zero value is coming here. So this is not equal to 0. Therefore, what we can conclude is that graph of f is a n surface. So this is how we are proving something is given to be an n surface or not. So repeat, for proving an n surface or not, what we have to do is, first we have to write your s as some f inverse of some c, that is as a level set. Next thing what you have to check is del f of p not equal to 0 for every p belongs to S. When these two condition holds, means we will say that your given S is an n surface. So we want to check a few more examples that we will check in the next video. Okay, thank you for your patient listening. Thank you.